Okay, so I promise you now we're getting closer to our answer on the blue sky, but there's one more piece you need to know. So we're talking about charges moving. We are talking about N2 and O2. We're talking about our upper atmosphere. And we are talking about molecules that look maybe like this. A positive nucleus and a little electron that's hanging around to sort of define the molecule. And we're saying even if you like, you can draw a little oval or circle around your whole molecule to sort of indicate it's a little bit of unit, which it is. Okay, one last piece to the puzzle now. So it turns out that if you're way above the Earth in the upper atmosphere, so here's the Earth again here. I wanted to do that in a more earthy color, like this brownish here. Here we go, or orange, or whatever it is. Okay, here's the Earth right here. Okay, and if you're going to be a molecule up there, say like here you are, here's your positive and here's your negative like this. Okay, the structure that we're saying is in the molecule. There's some interesting things that happen now, and this is sort of the last piece. When we were discussing a charge that was all by itself, and I'll just draw it for the last time here because we're coming to our conclusion. Remember the charge that was sort of looked like this with all the electric field lines going around it. And we said that when a light ray comes in like this, it'll get this charge moving up and down and up and down and up and down. I showed that to you several times. And of course, what can happen, I'll draw in a slightly different color, is when this charge starts to move up and down like this, it starts to generate its own light rays. Looks like a big spider, had all those squiggly lines coming out. Remember? Well, one thing about this charge here is this is a so-called free charge. And it's called a free charge because it's not connected to anything. It's just sort of all by itself. Okay, it doesn't have another charge around it. It's not bound to a nucleus. It's not in a molecule. It's just sitting here all by itself. And when you're a free charge, when some sort of light wave comes in, you're free to move as quickly as you can to keep up with that light wave, the way I showed you in a few videos. Remember when the up and down went by, the charge went up and down as well. But it's a little bit different over here in nitrogen and oxygen because you do have the charges just like this one, but the charges in these molecules here, as you may know, are bound together, okay, because it's a molecule. So we don't have a free charge situation anymore. And so it turns out one of the consequences of that is that it doesn't always move in response to a light wave. Sort of exclamation point. So you're like, wow, really? Yes, really. It doesn't always want to move. The free charge always moves no matter what. But when you start to get bound and stuff like that in here in a molecule, you start to develop your own properties and your own structure. And that's what chemistry is about, is molecular structure and things like that. And one of the consequences of being bound together, one of the consequences here of being bound together is that you don't always move in response to a light wave. So let me tell you how nitrogen and oxygen behave now. Okay, so we have the sun over here. So here's the sun, that big ball here, here's the sun. Then of course all these light rays are coming out. And I'll dispense with the white for a moment because we know what white light is actually a combination of a bunch of colors. So inside the sun's light, there of course is blue light, and there is red light, and there is green light, and there is orange light, and everything in between is sort of flowing out of the sun. That's what white light is. White light is a combination of all these different colors here. We'll talk about it a bit more when we talk about rainbows. And so here's what happens. The molecules in the upper atmosphere are getting hit by all of these colors. They are getting hit by the red. They are getting hit by the orange and the greens and the blues. All of these colors are hitting the molecules. But guess what? Because they're bound together, they don't always move in response to a light wave. It turns out that the red light, and we can draw a little wiggle on it if you want, like that, the red light wave that's coming in like this is going to go on by, and guess what? The molecule is not going to respond very much. It's just going to let the red go on by. It might start to move a little bit, but not very much. Guess what else? When the orange light wave goes by, like this, wiggling on by, molecule might move a little bit, but not much. The free charge would be going crazy. But the molecules does not, because it's bound together and doesn't always move in response to all light waves. The green one's going to come through. Here comes the green one, come through like that. And for the most part, it's going to go by, although I will say probably for the green, the molecule is going to start to oscillate a little bit more. And what I mean by oscillate now is, again, the charges are going to start moving. So in response to the green here, where maybe the molecule all by itself sort of looks like this, when it's hit by green light, it might start to stretch a little more, and it might start to sort of collapse a little bit more, and it might start to stretch a little more. It might start to make that oscillating motion. So something like that. It might start to do that a little more in response to the green light. But when the blue light comes through from the sun, when the blue light hits the molecule goes absolutely crazy in terms of its motion. So if you get this blue light wave from the sun coming through and hitting you as a molecule, you are going to get really small like this. Then you're going to get really large like this. And you get really small again and really large like this. And then really small again. You are just going to absolutely go crazy when that blue light comes through. And you can sort of see where that wave is right here. It's up, then it's down, then it's up, then it's down, something like that. And that's exactly what the molecule is going to do. So if you get this molecule moving like absolute craziness in response to blue light, blue light from the sun, again, not the reds, not the oranges, not the greens, but the blues, then you're going to start wiggling like crazy. And what happens next is that you start generating your own light rays. We discussed that a couple times, that a light that can come in can cause a molecule to generate its own light wave. And of course, the color of the outgoing light waves will also be blue. These molecules, when they get hit by blue light, will start generating their own blue light that's going to go in all directions, just like that moving charge that I showed you in a previous video like this. But it's going to be blue now, because if you're stimulated with blue light, you are going to start making your own blue light. And this picture here that I've just drawn of this oscillating molecule here with all this blue light coming out, this is our final piece then for why the sky is blue. So let's wrap it up in the next video.